hope I can make the presentation as long as the CV. This session is set up for a longish period of time, slightly shorter now that we're starting a little later, but I really don't want to talk for the majority of that. I will give a presentation to kind of set the scene, to establish what types of evidence there are, and more importantly, how do we go about sifting the evidence? How do we decide, what evidence is valid, and at what point have we established scientific proof of various processes? And then I would expect that the remainder of the time we actually have an open floor, both Q&A, if there's things which are unclear to you, or you wish to explore them further, or if you wish to give your own viewpoints on this, we should have that as a discussion. So that's the agenda for this morning. Hello, that's not working. So really the issue here is that the global climate system has internal dynamics. It has variability due to the fact that it is a complex system, and I'm using that in a very particular sense. It doesn't mean that it's the same thing as complicated. Yes, it is complicated as well, but complex in its kind of complex system sense means that there are feedbacks and there are nonlinearities, and the combination of those feedbacks and nonlinearities, also inertias, time delays, means that the behavior has dynamics which is internal to the system. It doesn't need to be stressed from the outside. It can have variation for purely internal reasons. On top of that, the global climate system is subject to various external forcings, which are natural in origin. There's the variations due to the fact that our orbit around the sun isn't perfectly circular, so it has an elliptical shape. The exact shape of that ellipsis changes. Also, our axis is inclined relative to perpendicular to that plane of orbit, but it isn't exactly at 23.5 degrees. It has a little wobble in it. These things all add up and vary the amount of solar radiation we're receiving. The sun itself has internal dynamics as well. That's why we have sunspot cycles and various dynamics in the sun. So the type of energy that the Earth is receiving is also varying. So there's a whole bunch of things going on which cause the climate of the Earth to vary on various time scales, day and night, through the year, over a period of several decades, and over periods of tens of thousands of years. So we know that that's going on, and we've known that that's going on for a long time, and we have lots of proxy records for that, and we understand the kind of dynamics of that reasonably well. Then on top of that, there is a human forcing. So now you've got a signal-to-noise problem. You've got a certain secular trend, a directional trend over the last period of time against a natural variation. And it's a problem of how do you untease which part of this is natural variation and which part of this is due to human effects. And that's really what the essence of this discussion is about. And really the approach that we take is quite nicely summed up by Sherlock Holmes, aka Arthur Conan Doyle, where he says, when you've eliminated the impossible, okay, whatever remains, however improbable, must be the truth. And so we go about taking out of this variation everything that we understand causes variation. So we account for that. We account for the orbital variations. We account for the effect, for instance, of volcanoes. Everything that we know has an effect on the climate, you take that out and then you're left with a residual variation. And then you try and see what explains that residual variation in the most plausible way. So the first is the data. And if we accumulate data from sources all around the world over the period of the 20th century. So the first actual records of the global climate date to about 1850. In fact, one of the oldest ones in the world is in South Africa, and it's wonderful to go to the South African Observatory in Cape Town and go into their library. It's this wonderful old Georgian building, and you go in there and there's these kind of wood-paneled, glass-fronted bookcases with all these ancient books in them, and there you open one of the bottom cupboards and you take out this leather-bound journal and open it up. On page 1 and written in the most beautiful copperplate handwriting is kind of record number 1 from the weather station at the Cape Town Observatory. Of course, that particular weather record is no longer usable because now Cape Town has spread all around it. It's no longer a good representation of that location. Okay, but you put together these weather records going back as far as you can. Effectively, you can't go back really well before the beginning of the 20th century because the records just get too sparse. But from then onwards, there's quite a lot of stations that you can do. And when you assemble this worldwide, it is tens of thousands of stations go into this analysis. That, of course, is only a quarter of the world. That's just the land mass of the world. Much of the climate system of the world is the oceans, so you need to have an equivalent set of measurements from the oceans. Well, fortunately, although we don't have weather stations there, we have ships of opportunity, and many, many, many ships, as a routine, keep the record of the weather as they're moving around the world. And you've got to then assemble that, where was that ship at that time, and put it together. And there are some peculiarities in that data set as well. For the first, several decades of that, when they took ocean sea surface temperature, they threw a canvas bucket overboard on a rope. And you pulled it up, and by the time it got up to the deck where you were measuring it, that canvas bucket had actually cooled down evaporatively. So there was a systemic bias in it. So there's all kinds of these complications that go in. But you assemble this information from all over. Tens of thousands of locations over a century, daily records. It's very, very large data sets. Now you can't simply say, well, it's a big data set. The law of averages will come to my rescue. Let's just, hit the average button and work out what the global mean temperature is. You can't do that because it is not spatially representative. For instance, you might have 10,000 records, but 9,000 of them are in Europe and the rest are scattered around. What you're really measuring is the temperature change in Europe. You're not measuring the temperature change in the world. So you have to go through a whole series of processes that then, weight these spatially so that you've got an even coverage around the world. You have to filter them for things where there has been changes, for instance, through urban heat islands. You've got to check them for instrumental discrepancies. For instance, the one that I mentioned about the bucket overboard, you see a sudden change when you change, global standard instruments, etc. So all of that goes in, and you eventually end up with this big data set, which is the basis of this kind of analysis. If you look at the image on the left, that's the global observed temperature trend. So this is not a model, okay? It's an observed temperature trend over the 21st century, where all the colors, which are on the warm side are global warming, and the colors which are on the blue side are global cooling signals. And so if you look at that, the bits that are white are places where there's simply not enough records to make a consistent statement about. And the only place that's actually cooling in the entire world over the 20th century is there. Okay, that's a little bit just south of the of Greenland, and the reason for that is that remember that most of the heat in the world's climate system isn't in the atmosphere. It's almost all going into the ice bodies and into the oceans. And in that process, the ocean circulation is being perturbed. And that is a consequence of a greater upwelling of cold water just south of Greenland. But that's the only place in the whole world that is showing a cooling trend over the past century. When we do the same for the rainfall record, you don't get nearly as clear a picture. And there's a bunch of reasons for this. Rainfall is essentially a much more local scale process than temperature. You know, temperature rises at fairly large spatial scales and gets distributed with the wind circulation. Rainfall is, you know, based on convective storms in many parts of the world with a scale of only a few kilometers, and so you get this great patchiness. As well as which, globally, we have these very distinct kind of rainfall zones. We have the equatorial tropical rainfall area where the rising air, you know, causes a lot of rain to occur, and then that air descends outside the tropics in the subtropics areas, and that's why we have these desert bands across the Sahara and across the Kalahari. And so we have the spatial pattern in rainfall around the world under normal conditions. And when we try to look for trends over the past century, what we find is we do find some places with negative and positive trends, and there is coherence in it. So if there were no coherence whatsoever, if it was just dots all over the map, we'd say, no, we're just seeing noise here. But there is coherence, but it's not global coherence, it's regional coherence. And so if you look into these areas which are associated with the subtropics, we see drying trends, whereas in many other areas we see wetting trends over the last century. And that is reasonably consistent with our understanding of how the global climate system works. We know that a warmer world is a wetter world, and we know that from a lot of paleo records. So when the world was significantly warmer in the past, remember that in the last million years we've been through these Pleistocene, glacial, interglacials, and the glacial periods were globally drier and the interglacials were globally wetter. And if we go before that, before the Pliocene, where the world's temperatures were significantly higher, the world was also a significantly wetter place at that stage. So that's something we can say with a fair amount of confidence, that a warmer world overall is a wetter world, but that doesn't apply locally. Okay, so you can have exceptions to that. For instance, as the world warms up, we can get an intensification of the Hadley circulation, which is that tropical circulation, and that actually intensifies the drying along the subtropical areas. So it's possible to have warming and wetting overall, but drying locally, and it just happens that South Africa is located in one of those areas which is subject to drying. Right, but much more difficult to demonstrate a secular change in rainfall than it is in temperature, because the signal to noise ratio is so much higher. If we look at, for instance, the rainfall over South Africa, over most of South Africa, our interannual variability in rainfall has a coefficient of variation of around 30%. So that's what the natural variation is, 30%. And you're trying to detect a change of less than 10% against a background noise of 30%. Okay, that's really just a very hard thing to do. Oops, sorry, I'll keep on pushing the wrong button there. All right, so just another mention there is that this particular data set, which is one of 3 global compendiums of climate data over the past century and a bit, has come in for a lot of criticism from people who think that this is in some way fake data. Well, first of all, apply a kind of reasonableness test to that. In order to fake this data, you would have to have snuck in the dead of night, okay, into the observatory in Cape Town and fudged the data going back 150 years. And you would have had to do that in about 100,000 places around the world. Okay, is this in fact a reasonable hypothesis that you could do that? First point. But most of the criticism comes around the way this data is manipulated, massaged, in order to make it a homogeneous data set for testing. And there's a whole variety of things to do that. And there's a legitimate discussion about which interpolation processes you should use, which homogeneity tests you should use, etc., etc. And a bunch of people have said, no, we can do a better job than this, and have rushed off and built another data set. And they've all found the same thing. Okay. Similarly, when they say, no, you shouldn't apply the eigenvalue smoothing method, you should apply this method, they do it and they find the same answer. The details vary a little bit, but it's actually robust to the method that you apply to it. Okay, there is an underlying signal in there, no matter which method you apply to it. And we can have a debate about that. It doesn't mean that the data is false. Oops, sorry. So when we look into the specific data for South Africa, the stuff on the left there is stuff from South African data sets collected and archived by the Weather Service and analyzed a few years ago for the long-term adaptation strategy document. And you can see that the temperatures over most of South Africa in the period they chose to analyze, which was 1960 to 2010, because that's the period for which they had the data already digitized. In other words, collected in digital form. You see a general, warming trend with, for the maximum temperatures, an exception there, but a non-significant exception. Interestingly, amongst the minimum temperatures, general warming, but this interesting sort of structure of possible cooling over that period, over the high interior of South Africa. Which is, statistically significant. Interesting. I don't have an explanation for that. It's probably a real phenomenon. But one of the problems is only selecting a period from 1960 to 2010, because there are these kind of long-term fluctuations associated with the climate in South Africa, and that might not be a long enough period. So I'd always left this kind of analysis in the capable hands of my climatological, expert colleagues, and just accepted that they were doing a good job. But I would give this sort of talk repeatedly. I said, well, I actually better go and have a look at this stuff and just convince myself that this is a real phenomenon. So I noticed that distribution of rainfall stations is really, really quite sparse. In South Africa, that's in fact temperature stations. South Africa actually has about 1,000 weather stations around the country. Why are we only representing, 15 or 20 of them there? Well, it's simply because, the stuff hasn't been analyzed, okay? And much of the older stuff hasn't been captured.